Right, so before we continue with the main definition, so let us recall that the most general form of a first order ordinary differential equation is when the left-hand side is the derivative of the unknown function, and the right-hand side is some expression that involves the independent variable and the unknown function, right? So here are a few examples, right? So of course sometimes it doesn't actually feature y or t, but sometimes it has both y and t, but as long as the right-hand side does not contain, say, the second derivative of the unknown function, or as long as it doesn't contain, say, unknown function evaluated at some other point, or some integrals of the unknown function, or whatever. So as long as it relates y prime of t, y of t, and t, it is fine. It is an first order ordinary differential equation. So let me maybe emphasize this, that this is important, that this y is actually y of t. And this dy dt is actually y prime of t. Right, so for example, if the right hand side contains y of, I don't know, t minus 1 or something like this, that is not the case, so that is not allowed. Right, given first order differential equation, its direction field is the vector field that is constructed according to this rule. Recall from calculus 3 that a vector field is it assigns a vector to every point on the plane. So at each point of the plane sits a vector, and the coordinates of that vector are calculated according to a certain rule. So in particular here, so the rule is that given a differential equation, the first component of the vector is always 1, and the second component is always f of ty. So let me give you an example, right? So suppose that I want to look at a point when, say, at this point. So suppose that t equals, I'm sorry, it's not really t. Suppose that t equals 1.5, and then y here equals 5.5. So let me show it more clearly. Right, then the right hand side of our differential equation, which is this, and so f of t y is going to be 9.8, and then instead of t we substitute 1.5, and instead of y we substitute 5.5. Right, 2 times 5.5 is 11, so 9.8 minus 11 is minus, what is it? 1.2. So it means that at this point the vector that we should plot is the vector with coordinates 1 and minus 1.2, right? So let me, it is something like this. So this is 1.2, this is 1, and the vector looks like this. So the coordinates of this vector are 1 and, sorry, minus 1.2, of course, minus 1.2. That's why it points a little bit downwards. Right? So the vector that you see on this direction field, this vector is actually, I mean, of course, if I plot the whole vector, then I would have to do this. so that its x coordinate is 1. But I just plot a vector that is parallel to it, but much shorter, so that different vectors do not overlap. Right? So this vector that sits here is parallel to the vector with coordinates 1 and minus 1.2. And of course you can do the same thing at every point of the plane. This is how you calculate the direction field. Okay, so for your reference, so there is a MATLAB or Octave code that plots this vector field. Then, why is it so important to talk about this direction field? So the reason is because a direction field is a very convenient way to visualize a differential equation, right? Because what it tells us is the following. So remember that the geometric meaning of the derivative is that it is the slope of the tangent line, right? So it means that if we plot the graph of the function y of t, then y prime is the slope of the tangent line. But at the same time, the slope of a vector is its y component divided by its x component. So here, if the x component is 1 and the y component is f, then the y component divided by the x component. And so this is x component, this is y, so then y over x is precisely f of t y. Now, so in other words, the differential equation tells us that the direction field is tangent to the graph of the solution at every point. So informally, you can think of it means that when you plot a solution, and the solutions kind of follow the arrows. So, for example, if you want to plot a solution here, then it will follow all the arrows here. So this is a solution, right? But say, I don't know, so these this would not be a solution, right? Because the blue line does not really follow the arrows. So the reason is because if you plot this tangent vector at every point of this solution, then it will exactly be the tangent vector that the vector that we calculate according to the rule of the direction field, right? And I've prepared a little web demonstration for you if you want. Hope it is going to work. And so it plots the direction field of a particular differential equation, but you can play with it a little bit. Yeah. And so for example, you can add y of 0, say, I don't know, y, let's enter maybe 2. No, 12 is too much. And enter 2. And you can enter the value of t, so let me, enter, I don't know, say 0.5. Right, so it means that this system plots the differential equation. Here is the differential equation. dy dt equals t minus y plus 1. Right, so it means that here our solution passes through the point where t is 1/2 and y is 1.7. So this blue point is 1/2, 1.7. And then if at this point you calculate the right hand side of the differential equation, then you will get, so t minus y plus 1, right? So you will get 0.5 minus 1.7 plus 1, so which is minus 0.2. And so this black vector is the same as the vector from the vector field underneath, and it is parallel to the vector where the first component is 1 and the second component is minus 0.2.